Welcome. We're now going to approach problem 2 on discussion 6A Spring 2018. So question 2 talks about some more countability. In particular, when we start looking at part A of question 2, we are talking about the countability of an infinite continuous interval of the real numbers. And without loss of generality, we assume the interval 0 to 1. And we want to make a bijection between this interval and all the positive reals, if we can, which are defined to be 0 to infinity. After this problem, we'll see that, in fact, you can make a bijection between any continuous interval of R, a to b, and all of the real numbers, not just the positive ones. But for now, let's focus at this particular question. So, OK, the idea is I have this subset from 0 to 1, and I want to map it from 0 to infinity, right? So all the way out. So in some sense, you're mapping this all the way here. So what we're going to try and do is we're going to try and invert every number in here, right? So the most natural function I would think of first is I would say, OK, take some number x and send it to 1 over x. So what happens then is this interval of ours from 0 to 1. Now, the point in the middle, so say 1/2, gets sent to 2. The point a little closer, so say 2/3, gets sent to 3/2. And so you can see everything in this range will get sent to everything in this range. But then you can see that the closer you get to 0, the farther out you get. And in particular, 0 gets sent all the way as a limiting case to infinity. And you end up covering everything from 1 through infinity. So intuitively, this looks like something good. However, I don't want to map into 1 through infinity. I want to map into 0 through infinity. So instead, so let's call this f1x. So finally, when I make my function f of x, I will make it as 1 over x. But then I will shift everything 1 to the left. So I will go -1, right? And we can make the same mapping and check 0 still gets sent to infinity. So that's fine. And then you have, say, 1/3, which now gets sent to 2. And then you have 1/2, which gets sent to 1. And then 1 gets sent. And you covered the entire interval. OK. So that was the intuition behind making this bijection. Now we're going to go ahead and prove that this is, in fact, a bijection. Now, in proving something is a bijection, so in proving f, in this case, from 0 to 1 into the real numbers is a bijection, we have to prove two things. First, that f is 1, 1, which means that whenever f of some number, let's call it x, is equal to f of another number, let's call it y, then it follows that those two are really the same number. What this is saying is every element here and here, they go to separate elements over there. So everything in your domain gets mapped to something unique in your range. So let's prove that. Well, f of x is just 1 over x minus 1. If this equals f of y, which is 1 over y minus 1, then it must mean that 1 over x equals 1 over y. And since x and y are both non-zero, I can multiply on both sides. When I multiply on both sides, I conclude that this means x equals y. So everything in my domain gets uniquely sent to something in my range. So f is 1, 1. This is true. OK. 2, let's prove f is onto. What this means is everything in my codomain, which is all the real numbers, has a pre-image, which means there is some guy over here from 0 to 1, which touches a number here in R. And for every number in R, there is some guy which touches it, right? So that's the intuition behind what being onto means. Mathematically, the definition lends itself to being, if we say f is onto, then we're saying for every y that you pick in your codomain, which in this case is R, there exists some x in your domain, which is 0 to 1, such that f of x equals y. So let's prove this. pick a y belonging to R. Let's just call it, so let's call it y. So now you have y belonging to R, and you have some x, so you'll have 1 over x minus 1, and this should go to y, because I want f of x equals y. And then you get that x is 1 over y plus 1, right? And you can plug this back in and check if you plug this back in, you get that 1 over x is y plus 1, and then minus 1, so you get y. Now, this number, for all y greater than 0, this x is strictly between 0 and 1. So you can verify that. And now we have that f is onto. So this has been proven. And then we conclude that f is a bijection. OK. And if we have a bijection between this set here and this set here, this implies that the cardinality of this set is the same as the cardinality of the positive reals. In particular, you can also go on to show as a fun exercise that this is exactly the cardinality of the reals, right? And the final thing that I'd like to say is you can take any subset of the reals in a continuous range, say a to b, and make a bijection from this to the reals. And intuitively, what you're going to do to make this bijection, I'll leave out the algebra, is you take a to b and you shift it to the origin. So you shift it so that now it's around 0. And in the same way that we did here, you map this portion onto the positive reals, and you map this portion onto the negative reals, right? So I'll leave that as an exercise. OK, so now let's look at question 2, part B. Now, this might have been something that you might have seen when we're trying to establish whether the set of all computer programs is countable or not. And a similar argument is held even there. So the question says that I have a set, let's call it S, which has all strings in the English alphabet. Now, this is an abstract notion to work with, so I'm going to make some notation to clarify things up. I'll let A be the set of alphabets in the English language. So it's A, B, C, D, so on till Y, Z. OK. Now, S is really just A to the K for all K belonging to natural, right? So what this is saying is it's the set of all single letter strings. And this is the union over all K. So there's a set of all single letter strings, and then all double letter strings, and then all triple letter strings, and so on. So you can see, for example, the string A, B, E, G would come under the alphabet 4, right? Because you have 4 guys each from this alphabet. OK. And now the question is S countable? The intuition that we're going to work with is, well, I need to find some sort of an enumeration for S. And we'll see in a minute that the notation we've established would actually make the enumeration very easy to follow. So my claim is that, yes, S is countable. And the enumeration or the listing that I'm going to give is as follows. So I'm going to say to list S, list A1. Why do I know A1 can be listed? Because A1 is finite, right? It's just all single letter strings, so I'll list them all. Then list A2. I know I can do that because that's a finite length set, because all the 2-letter strings in the English alphabet are a finite number of them. And then I say, OK, now list A3, and so on. Keep doing this. And if I keep doing this, because eventually I list A to the K for all K, I would have listed every element in S, right? Intuitively, what this is saying is you write out the strings A, B, C, dot, 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 till Z. Then you write out double A, B, dot, dot, till A, Z, and then BA, dot, 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 till BZ. And then you do this till you do ZA to ZZ. So these guys are all the 2-letter strings. And then you do it again for all the 3-letter strings and so on, all the way till ZZZ. And now you do all 4-letter strings, and then you do all 5-letter strings, and so on, right? And you can see that because we enumerated it in this way, we will eventually hit all the K, which means every string in the English alphabet would at some point show up in this enumeration. And by definition, anything that you can make a list of is countable. The list itself is allowed to go on forever, but there is a definitive order to this list. And then it follows that, yes, S is in fact countable. Now let's talk about question 2, part C. Now this builds upon our previous part, and it says that it's the same thing as before, except this alphabet that we now have A. In the earlier case, so earlier, A was A, B, C, till Z. So in particular, it was finite, and this let us make a very nice listing of all my strings. Now, my alphabet A is no longer finite, but it's not the worst kind of infinity to deal with. It's some A1, A2, some A3, so on, infinitely, but it's countable, right? So the key argument that we will make use of later on is that even though A is not finite, but it's countable. OK, and we construct the set S as before. So we say S is again defined to be the union over all k of A to the k, where k is a natural number. This is just saying all finite length strings from the alphabet A. The finiteness lets us write each string as A to the k for some k, which is basically saying it's a k letter string, right? Each letter is picked from this alphabet A. OK, and then again the question is S countable? And once again, this time it's a little less intuitive, but my claim is yes, S is in particular countable. The enumeration is, I don't find it particularly intuitive. Yes, S is countable. And the enumeration looks something as follows. And then this is a very nice result that you can also, as an exercise, try to prove using what we've seen in homework, which is that a countable union of countable sets is itself countable. Right? So there is the other way to prove it, because we say, look, each of the A sub k's, so there is another way to prove it, where you prove that A raised to k for all k is countable, and then a countable union of that is also countable. But for now, we will explicitly list out the enumeration we use. And the algorithm for doing that goes something like, so let's try and see what will fail if we do the same algorithm from last time. Last time what we did is we said, look, list all strings of letter 1, then all strings with 2 letters, then all strings with 3 letters, and keep doing that. But now if you list all strings of 1 letter, there will be countably infinite of those, right? Because you list A1, and then you list A2, and then dot, 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 dot. But you'll never stop, because A goes on, the alphabet, capital A, goes on forever. So that's not OK. You could list all the strings containing A1, the letter, this thing, but that would go on forever as well, right? Because you do A1, and then you'd make 2 A1s, and then you'd make 3 A1s. But then where do you stop? So turns out that doesn't work either. This algorithm needs a little bit of skill, where what you say is you restrict 2 things at a time. So just restricting the number of letters is no longer enough. Just listing which subset of the alphabet you can use is no longer enough. But as it turns out, if you restrict both the number of letters as well as which alphabets you're allowed to use, the listing is possible. So what you say is, you say list all 1-letter strings, but I will also restrict the alphabet, all 1-letter strings with only A1 in them. So trivially, this is just the string A1. But now I say all 2-letter strings with A1 and A2 in them. So that would be the string A1, A2, A1, A2, A2, A1, 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 and A2, A2, right? And I say all up to, right? So maximum up to 1-letter strings, and in this case again all up to 2-letter strings, and then I get all of these, and I say remove all the duplicates, right? So I've already seen A1, so get rid of that. And in general, I repeat, so I say all up to 3-letter strings with A1, A2, and A3. So these strings are going to be something like first all 1 letters and then all 2 letters. So A1, A3, A3, A1, A3, A3, and so on, right? And up to 3 letters. So you can see each of these cases, when you take only 1 letter with only A1, that itself is finite. You do only 2 letters with A1, A2, that itself is finite, and only 3 letters with A1 through A3, that itself is finite. And then you can see that any string that you make, so say you make the string A1, A5, A7, A8, A2, A2, and A7 again. This will be listed when you're listing strings of length 7. No, so this will be listed when you're listing all strings of up to length 8 using A1 through A8. And then you can prove that any arbitrary string you take will show up somewhere in this listing. And then it follows that this listing covers all of S. And now that we have a listing covering all of S, we conclude that S must in fact be countable. And then we have proven the enumeration that we require.